Hello, welcome back to Educator.com and welcome back to physical chemistry. So today we're going to continue our discussion of the first law and energy and work and heat and things like that. We're going to start talking about changes in energy and state. And in this particular lecture, we're going to be talking about constant volume processes. So we're going to start putting some constraints, either constant volume, constant pressure, constant temperature, things like that, to see if we can learn some things about what's going on with the first law and with energy. So let's jump right on in. Okay, so let's recall. Guess we'll go with black today. So U, energy, is a state function or a state property. It does not depend on the path that you take. It just depends on your beginning state and your ending state. That's it. So if I start at 0 feet sea level and I go up, let's say, 500 feet above sea level, the difference is 500 feet. It doesn't matter whether I drop down to negative 300, then go up to 800, then come back to 500. All that matters is the beginning and ending state. Now, work and heat are not state functions, they're path functions. So W is a path. There's a little more, less room. We could probably squeeze a little bit more information onto a page here. So W is a path function or a path property. A path function, and heat is also a path function. So a path function, its value, the value of work or heat, depends on the path that we take. If I'm going from here to here, this involves less work than this, or this, or this. The amount of heat from here to here is going to be less than the amount of heat like that. So it depends on the particular path that we take. Now, the first law is this. It says that the change in energy, the total change in energy of the system, is equal to the heat gained by the system minus the work lost by the system. That's all that is. So we'll often use this form. This is the fully integrated form. We'll often use the differential form, because again, we're going to be leaning much more on the mathematics and on more sophisticated mathematics. So du equals dq minus dw. So the differential change in energy equals the differential change in heat minus the differential change in work. Now, a quick word about this. Again, U is a state function. W and Q are path functions. The symbolism that I've used, this d, it tends to imply that they're the same. They're not the same. Many books will differentiate notationally a state function and a path function. They'll use this differential notation, the standard one that you're used to, the d, for a state function. And they'll use some variation of that for a path function. You'll often see something like dw, the small Greek delta, and dq, or you'll see d with a line through it for dw and dq. This lets us know that these are path functions. More specifically, from a mathematical point of view, they're inexact differentials. So a state function is an exact differential, and a path function is an inexact differential. And we'll be talking more about what we mean by exact and inexact and the properties of exact and inexact differentials. I myself, I don't like to differentiate because I believe, physical chemistry and thermodynamics, there's already just an abundance of symbolism as it is. To introduce new symbolism, it just confuses me. It's just, me personally, it's just easier to remember that work and heat are path functions and energy is a state function. That's it. Other than that, it really shouldn't cause you any problems. So I'm going to go ahead and use the same, but they're not the same. This is an exact differential. These are inexact differentials. Okay, so let's go ahead and talk about, you know what, let's just stick with blue here. So, integral from an initial state to a final state of this equals u2 minus u1. This is the fundamental property of a state function, that it integrates the way you're used to according to the fundamental theorem of calculus. It's equal to delta u. This is an exact differential. So exact differentials integrate like this. You take the final state minus the initial state of the integral of that particular function. So exact differential. This is a state function. Now, when we integrate heat, let's say dq, we don't get q2 minus q1, we just get whatever the value of q is. Okay, this is not delta q. This is an inexact differential. Inexact differentials do not integrate the same way exact differentials do. They do not follow what this final minus initial. Okay, they depend on the path. So you just get a quantity. That's it. Path function. Okay, now let's see, dq. dq, it doesn't make any sense because a system does not possess heat. Heat is something that shows up during a change of state. Heat is actually a process. When there's a temperature differential of a system and a surroundings, or two systems, whatever it is, heat is the transfer of heat. It happens at the boundary. That's what's going on. A system doesn't possess heat. A system has a certain temperature. Temperature and heat are not the same thing. Heat is what happens during a change of state. So it makes no sense to say that there's a certain amount of heat in the beginning, a certain amount of heat in the end, and the change in heat is the difference between the two. That doesn't make sense. A system does not possess heat. Granted, we tend to be a little loose with our language usage. We often will talk about heat as if the system does possess it. That's just part and parcel of the historical discussion of thermodynamics, the sort of looseness in language that exists in science in general. It's not a problem as long as you remember these things. Okay, so delta Q makes no sense. Makes no sense because a system does not possess heat. And the same thing with work. When we integrate the differential of a work, okay, from one state to another, we're adding up all the work done along a particular path, we get the final work. It's equal to W. It is not equal to dW, because a system does not possess work. It does not make any sense. So again, work, inexact. Exact. Path function. So dQ makes no sense. dW makes no sense for the same reason. A system does not possess work. Now, notice, here's what's interesting. That Q and W are path functions, yet their difference is a state function. That is extraordinary. That is truly amazing. Q and W, they are path functions. But their difference or sum in a different convention, the chemist's convention, we usually write Q plus W, but our convention is Q minus W. But their difference, I'll put sum here, is a state function. That's amazing. It's truly, truly amazing. State function. Energy. Okay. So, now,